Hello everyone, my name is Laura Miller and I'm a postdoctoral research fellow at the University of Glasgow. I'm very sorry to not be there with you today, but I'm delighted to still present to you my talk on the micromechanical analysis of the effective stiffness of poroelastic composites. For anyone that has any questions about my talk or would like to discuss this work further, I've put my email address here at the bottom of the screen. So since my talk is on poroelastic composites, I thought I'd begin by introducing what porous media actually are. So in this image here, we have a poroelastic material. So we see that it comprises an elastic matrix, which is shown in white, with all these interconnected pores where the fluid will percolate through the structure. So this type of material is typically modelled using Biot's standard poroelasticity. And this is a macro-scale system of governing equations that was first derived by this reference 1 that I've provided here, who are Burridge and Keller. And what they did is they derived this system from the microstructure. So that means they incorporate all the tiny little microstructural details in the final system of governing equations. This type of a modelling framework can be applied to many scenarios, such as rocks and soils, which were the initial applications in mind, through to nowadays, more recently, biological tissues, artificial constructs, and biomimetic materials. So I've provided here a picture of human bone. So in human bones, when you zoom in, you find a collagen and mineral matrix through which fluid flows in the pores. So this is an example of biological tissues that are poroelastic. So my work is on poroelastic composites. So the difference between a poroelastic material and a poroelastic composite comes in the details in the microstructure. So in a poroelastic material, they assume that the matrix is just completely homogeneous, that it's made of one complete material. In our case, we've extended this to assume that the matrix can include a variety of elastic inclusions. So I set up my model based on I choose a sample of tissue, create a schematic of what its microstructure is, and then associate that microstructure as a repeating unit that forms the whole tissue. I then set up a fluid structure interaction problem on this microscale, and then use techniques to upscale that to get equations that govern the whole material. So this is exactly what I'll now explain to you here. So I've got a sample of human tissue here. So this is the interstitial matrix in human tissues. We see that when we look around one section, we see the pink elastic matrix, this included elastic cell, and a fluid-filled pore. So this is exactly how I've made up my microstructure here. I have my red elastic matrix, my blue elongated fibre or subphase, and in white, we have the fluid flowing in the pore. You'll also see that I've associated a length scale to this structure. So the length scale is small d, and this is very small in comparison to the length L that's associated with the whole material. So even though this is a 2D image, we assume that these are 3D cells that when repeating over and over, create our whole tissue. So I'll now explain how we set up our fluid structure interaction problem. The first thing that we require is going to be a balance equation in each of the domains. So I'll start with the solid ones. In the solid ones, we have the balance, the divergence of T1 and T2, where T1 and T2 are the solid stress tensors in each of the phases. And these comprise C1 and C2, which are the fourth rank effective elasticity tensors that describe each of the individual phases separately. Then we have this Xi of U1 and Xi of U2. Well, Xi is just our symmetric part of our gradient operator, and U1 and U2 are the elastic displacements in each of the phases. Similarly, for the fluid, we require a balance equation for that. So we have the divergence of this TF. Our fluid is a Newtonian incompressible fluid, so it has the constitutive law given here, where P is our pressure, mu is our fluid viscosity, and the Xi of V is just the symmetric part of the gradient of our fluid velocity V. Since the fluid is incompressible, I also have written down this incompressibility constraint here. So that's the governing equations for each of the compartments. But to close the problem, we're also going to require some interface conditions. So I've zoomed in and made our picture a bit bigger here so that it's clear each of the interfaces that we have. So we have gamma 1, gamma 2, and gamma 3. Gamma 1 is our interface between the elastic inclusion and the fluid, and across that we impose the continuity of velocities. So U1 dot is the solid velocity and V is our fluid velocity, so that's their continuity on gamma 1. And we also impose the continuity of stresses between the inclusion and the fluid. We do a similar thing on gamma 2, which is between the matrix and the fluid, and shown in black here. This is our continuity of velocities and stresses. And then on the solid-solid interface, that is between the inclusion and the matrix, we have the continuity of elastic displacements and the continuity of the stresses. So this is now a closed problem. So what we can do, that's a full fluid structure interaction problem. We want to suggest a technique that can be used to upscale from a fluid structure interaction to a whole system of macro-scale governing equations. So we can introduce this scale separation parameter epsilon. And I mentioned before that our microscale has a length d and our macroscale is a length L. This separation parameter epsilon is just the ratio of those two lengths. So since our microscale is just one small part of the whole tissue, we can we then know that this ratio of d over L will be much less than 1. And this motivates the application of the asymptotic homogenization technique to upscale the problem. So I won't go through all the steps of this technique as there is not time for that, but for anyone who's interested in the detailed steps, the paper that I've just referenced on the previous slides contains all the steps. So I'll give a few summary details of the technique, however. So we propose two different variables, a variable x that captures the macroscale and a variable y, which is meant to capture all the microscale variations of the fields. Now, each of the fields we assume is a function of both the macroscale and the microscale and are y periodic. Now, the fields, I mean that as in things like the elastic displacement, the velocities, the pressures, that we just introduced in our fluid structure interaction problem. So once we have done that, we perform a multiple scales expansion in a power series of epsilon for every field that is in the fluid structure interaction problem. Once we have written that expansion out, we can equate coefficients of powers of epsilon. That is, we equate powers of epsilon to the 0, epsilon to 1, and so on. And using those, we form microscale cell problems that we will eventually solve to find the model coefficients and that we can use to form the actual macroscale governing equations. So if we complete all these steps, we arrive at our macroscale model. This is my new model for poroelastic composites. So it's governed by 4 equations. First of these is our Darcy's flow, where W is a relative fluid solid velocity, and this capital W that I've shown in pink here is our hydraulic conductivity tensor for the fluid flowing in the material. We also have a balance equation and a constitutive law. Our constitutive law has 2 parts. It has this blue part, which is an effective elasticity tensor. And what it does is it captures the changes in the elastic properties at different points in the microstructure. And this is the key difference between our new model and standard poroelasticity. In standard poroelasticity, it would be assumed that there is only one elastic phase, so you would only see one of these elasticity tensors. You wouldn't have the option to have the variety of additional ones, as well as these tensors M, which capture the variations at different points. We also have this red coefficient here, which is actually related to the Biot's tensor of coefficients. And we also have a conservation of mass equation. That conservation of mass equation comprises this blue coefficient, which is our Biot's modulus, and this orange part, which is our true Biot's tensor of coefficients. So we can prove that this model is truly, formally and substantially of poroelastic type by proving a few properties. The properties are that we have a relationship between this orange coefficient and the red one here. The relationship is that our Biot's tensor, this orange one, is equal to the negative of this red one. This is also very useful numerically, as when computing these coefficients, The problem that is used to find Q is different from the problem that is used to find M. Now, by these two coefficients being equal up to a negative, we can solve only one of the problems to determine both coefficients. We also can prove that this light blue coefficient M, the Biot's modulus, is positive, and we can prove that our effective elasticity tensor that I've written down here is major and minor symmetric. So we'll now move on to the numerical results. So I should say that what we're actually going to compute is going to be these effective elasticity tensors. So as they are capturing the local variations in the elastic properties. So what we've done is we want to see what the difference there is when you have actually included multiple elastic phases in your microstructure. So for example, if you take a sample of tissue and you image it using whatever technique, and when you're looking at the specimen, you find that you have different elastic phases and a fluid phase all together at the one scale that you're looking at it at. If you have my new model, you can instantly create a 3D geometry, and this was created in COMSOL Multiphysics, where you have a matrix, an inclusion, and pores. And you can set up any geometry you like that would resemble your sample of tissue. Then I've just taken a 2D cross section of this just to simplify and show more clearly exactly the structure we've got. And this is the effective elasticity tensor here that we will solve based on this geometry. Now, assume you've taken the same sample and you've imaged it and you see exactly 3 phases all together, but my new model hasn't been created yet. What would your next best approach be? Well, using what was already existing in the literature, the best that I can come up with is to do a 2-step approach. Now, the 2-step approach involves having simulations based on an elastic composite, where one of your phases in the elastic composite is fed in from information from porous media. So what I've done is, again, got my 2D schematic. I say that we have this composite where already the matrix has already been determined to be poroelastic previously. So again, I've written down here the effective elasticity tensors, as that's what we want to compute. And the our final CSP, which is our standard poroelastic effective elasticity tensor, requires us, first of all, not to just take input parameters from the 2 phases. We actually have to perform simulations to obtain the input parameters for the matrix. So to keep these simulations consistent, we assume that the 2 blue inclusions are both exactly the same volume fraction, same elastic tensors, which is why the C1s you see in both places are exactly the same. And we assume that the pores always have the same volume fraction when we're comparing them. It's just the scale at which they appear that is varying. So just to summarise what I've just said whilst looking at the picture, so we have 2 4th rank effective elasticity tensors that we're going to compute. So due to the geometry that we chose, tensors have 6 independent components each. Now this is because we chose uniaxial fibre elongation and uniaxial flow. This, however, is just a choice, just for a first example. These can be extended. We want to calculate the Young's moduli E1 and E3, and the 2 independent shears C44 and C66 for both of the setups. So these are our formulas for our Young's moduli, and these are determined by inverting the 4th rank elasticity tensors and then comparing with the material compliance tensor. Now these are written in Voigt notation here to cut down the amount of indices used for the 36 components of our effective elasticity tensors. So we'll start with some numerical results. First of all, I've compared the 2 Young's moduli, E1 and E3. So E1 and E3 using the Poroelastic composite model, that's my new one, are much lower. And we see that with increasing porosity, both models capture a decrease in the stiffness. And the effect of porosity is more prominent when considered at the same scale as the other elastic phases. So I wanted to actually really show the exact discrepancy that we're seeing between the 2 models. So I've just plotted this here. So we see that for E1, already at 5% porosity, there is a difference of 5% between the two model setups. And this increases to a 22% difference at 30% porosity. This is quite a dramatic difference, considering that we should be modelling exactly the same material using both models. And similarly for E3, at 10% porosity, there's already a 2.5% discrepancy between the models, and this rises to almost 10% at 30% porosity. So these are quite striking differences for two model setups that should describe the same piece of tissue. So here I'm doing a similar thing for the shear C44. So C44 using my new model is much lower. The effects of the porosity again are more prominent when considered at the same scale as the elastic phases. So I've provided in this table the thresholds at which each of the models should be used. So below 2%, for E1, both models provide basically the same result. For E3, this same threshold is about 8%, and for C44, it's approximately 5%. But these are quite low porosities, so to go beyond that, you're going to be seeing a significant difference between the two models, even though they should be describing the same material. This means that if you are modelling a tissue and you're using approaches that were designed prior to my work, you're going to be assuming that your material is much stiffer than what it truly is, based on the fact that you're not considering all phases at the same scale. So I've now also applied this model to the heart. So I'll briefly say a few words on that. So the heart is a muscular organ which has its wall, which is the myocardium, that comprises a variety of bundles of myocytes, collagen and elastin fibers, blood vessels, and pores. So this is very, very good description of poroelastic composite. So I've applied our structure that I've shown in previous slides here. I've got a bundle of myocytes in the middle, a matrix of collagen and elastin, and the blood vessels are going to be our pores in this case. Again, I've created the same 3D geometry as I used before, but I've considered this time a diseased case also. So when materials undergo myocardial infarction, the myocytes are deprived of oxygen, and this causes these cells to die. In the space where those cells die, we can't leave nothing. So the body produces a rich collagen matrix to bridge that gap where we've lost these myocytes. And this is what we account for in this geometry here, with this section of lost myocytes, and it's replaced with a stiffer matrix. So I considered, first of all, a healthy versus diseased using the model. And we see that the healthy is a much lower shear and shows a much smaller decrease with increasing porosity than the diseased case. The infarcted myocardium is a much higher E1 than the healthy case, almost double the stiffness. Now, this is exactly what you would expect to see, as an infarcted heart is usually much stiffer and therefore less efficient at pumping blood around the body. The stiffness of the infarcted case reduces dramatically with increasing porosity. Now, this is very interesting, as this can allow us to make predictions about reperfusion treatments that could be useful to create a more compliant heart for a more efficient blood delivery around the body. So we also considered what happens when we increase the volume fraction of our myocyte. That is also just increasing one of the areas of the elastic phases. So we found that in following myocardial infarction, you find that the myocytes surrounding the infarct region increase in volume to try and compensate and create a softer heart. So our simulations just back up this physiological finding. So C66 and E3 decrease with increasing myocyte volume fraction. The behaviour is consistent across the 4 fixed fluid volume fractions. The 4 volume fractions are 5%, which is underperfused, 10 to 15% is ordinary, sort of healthy perfusion, and 20% is overperfused. The typical healthy shear for the myocardium is approximately 10 kilopascals, which is much lower than the 24.2 that we're seeing here. So some final conclusions. For a poroelastic composite material with porosity exceeding 5%, then the discrepancy between our new model and the standard poroelastic approach when computing E1, E3 and C44 exceeds 2% and increases dramatically with increasing porosity. For materials with less than 5% porosity, a standard poroelastic approach or the LMRP model produce approximately the same results. The LMRP model should be considered as a valid alternative to a standard poroelastic approach when modelling a material with an inhomogeneous microstructure. And that's the most important takeaway message from the work that I've done. So in the future, it would be very useful to consider a much more complex geometry with additional fibres, fibre angles, and fluid flow in many directions. So thank you very much for your attention. If anyone has any questions or would like to discuss anything further, then this again is my email address for you to use. Thank you very much.